Okay, good morning, everyone. We can get started. Okay, so can everyone hear me?
Yes.
Yes.
Wonderful. And if at any time my audio cuts out, just let me know. And so today we're going to be focusing on ethers, Grignards, and organolithiums. So let's just get right in. So today's objectives, we're first going to look at how we synthesize ethers. I believe Bufon touched a little bit on ethers and thioethers on Wednesday. So we're just going to continue that with kind of the two main ways that we synthesize ethers. The first one being the Williamson ether synthesis, and then the second one being the alkene alkoxymercuration reduction reactions. And then after that, Brendan will take it away with hydrocarbon synthesis reactions. So, oh, that's not what I wanted to do. Okay, so if you guys will recall kind of what an ether is, right, it's just going to be kind of this functional group right here. And I hope you all had a chance to download the lecture slides. So it's just going to be this. We're going to have an oxygen between two R groups. And in this case, the R groups are going to be some kind of carbon containing compound. And so this is just kind of the general overview of how we synthesize these ethers using the Williamson ether synthesis. So we're going to first start off with something like this. And in this case, we're just using an alcohol, but we can also have a case where we use a thioether or sulfide, right? So we're going to start off with the alcohol, and then we're going to treat it with sodium hydride, which is this, which is going to be a really strong base. And then we're going to use an ether solvent. And all that's going to do is that it's going to deprotonate this alcohol and form this alkoxide with the kind of the spectator ion sodium. And then we're going to treat that with some methyl or primary alkyl halide, right? Something like bromine, iodide, or chlorine. And all that's going to do is it's going to do an SN2 type reaction. And this kind of alkoxide is going to add itself to the rest of our alkyl halide. And it'll look like this. So this is the kind of the starting alcohol that we had minus the H, and then this is going to be this part of our alkyl halide without the halide part. And that reaction mechanism is going to be really similar to the thioether synthesis, right? We can start off with the sulfide, and then we'll react it once again with that sodium hydride and ether solvent to get this the sulfur anion, and then treating that with whatever methyl or primary alkyl halide that we want to add. And it'll do another SN2 type mechanism to create our sulfide. And so let's kind of look at a couple examples of this. So imagine we start off with something like this. So pH, all it means is phenyl. You can think of it as just a carbon, a benzene ring attached to this carbon. And so we'll start off with something like this, and then we'll treat it with sodium hydride. And then for our solvent. And our product is going to be this. pH. Then we're going to get this kind of alkoxide right there. And that's going to also give us H2 gas. And if you'll remember from Wednesday's lecture, right, the H2 gas is going to be kind of that driving force of the reaction, because as the reaction goes on, it'll bubble out of solution. And so let's take a look at another example of that, or continue that reaction. So let's take this product and then create the ether. Just going to treat it with a primary halide. Let's do I attached to CH3. And then our product is going to be this. And then our byproducts is going to be the sodium with the I minus. And this will happen in a 90% yield. So these are really great ways to kind of synthesize those ethers that we've seen. And these ethers are going to be useful a lot of times for kind of solvent-based reactions. They're very unreactive, so they're great solvents. And so I mentioned that there's also going to be kind of this SN2 type mechanism to it. So let's say when we have our alkoxide, right? Just that this would be what we would have right after treating with sodium hydride. And then we take H3C with I, and then we just do that backside attack, right? And then we'll kick out the I. So we'll get ROCH3 plus I minus. And so I mentioned that this is going to be an SN2 type mechanism. And so what that's going to tell you is that the stereochemistry at that carbon, if this was a chiral carbon, the stereochemistry would end up being inverted, right? We would have the kind of this group, we would have it attached in the inverse of the iodide. And then, so kind of adding on to that, if I were to say, let's construct an ether like this. Right? This is just going to be CH3, 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 and then a CH3 like that. If I were to ask you, how would I construct this? Right? There's kind of two ways that we could do this. We could either break it down this way, where this would be the alcohol, or we could break it down the other way, where this would be the alcohol. Right? So let's kind of illustrate that point. So we could have something like this, where this would be alcohol, and then our CH3, like that. Or we could have something like this, where this is our alkyl halide, and then this will be the alcohol, the HOCH3. Right? And so these seem like theoretically they would both work to synthesize this ether that we're interested in. But actually, only one of these is going to work. And the reason behind this is because of the specific reaction type, the SN2 reaction type. And if we'll recall, right, SN2 reaction mechanisms, they're going to favor kind of the alkyl halide that's going to have the least amount of steric hindrance to it. So by doing kind of this reaction down here, right, as you can imagine, this is going to have a lot of steric hindrance. And because kind of trying to do that SN2 attack on a tertiary alkyl halide, because that's going to have so much steric hindrance, we actually won't see that product form. And there's no way that we can put these two things together and end up with this product. And so this is going to be kind of the way that you would get that product. So when we are doing these Williamson ether reactions, it's important to keep in mind that you want the alkyl halide that's going to have the greater SN2 reactivity, meaning that your alkyl halide, you want it to have as little substitution to it as possible to decrease that steric hindrance. Are there any questions on the Williamson ether reaction? Okay. So now we're going to move on to the second ether synthesis reaction. And this is going to be alkoxymercuration reduction. And we've seen examples of this already. So let's just formally introduce this. So let's say I have something like this. Right? We have just an alkene and we treat it with mercury acetate. So, and let's say we use a solvent like this. And so the way this reaction is going to work is that it's going to pretty much follow the exact exact reaction mechanism as our oxymercuration reductions. But instead, we're going to be adding in an alcohol instead of water. So right here, we're going to get this. And so you can see the ether functional group that we've just added into our alkene. So we started from this alkene and we got to an ether, but we're not done yet, right? And so what we're going to do is we want to get rid of this mercury product, right? It's not useful to us. And so the way that we get rid of that is that we treat it with a strong reducing agent like sodium borohydride. And what that's going to do is it's going to get rid of that mercury acetate and it's going to just replace it with a hydrogen. So our final product is going to be this, right? So this is kind of the overview of the alkoxymercuration reduction, and this is going to occur in a 91% yield. So this is also another great way to get those ethers. And we'll have these byproducts, mercury as well as borates. Okay. Now let's take a general look at the reaction. And so this is the general reaction mechanism, right? We're going to start with some kind of alkene, and then we'll treat it with our mercury acetate and whatever kind of alcohol that we're trying to add, right? So in this case, we just have ROH, and we're just going to add in the RO onto our alkene to get that ether. And so after kind of treating it with our alcohol, we're going to get rid of the mercury by doing a reduction with sodium borohydride. And this is going to follow kind of the same rules of regio selectivity and stereo selectivity as we saw with our oxymercuration reductions. And specifically by that, right, our stereo selectivity is going to be that our products are going to end up in a racemic mixture. And then our regio selectivity is that we're going to be attacking, or we're adding on OR to the carbon that's going to be more substituted, the carbon that would have formed the better carbocation. And so let's just write that down. The stereo selectivity is going to be non-stereo selective. And then our regio selectivity is going to be the Markovnikov. Right? We're adding OR to the carbon that's more substituted. And let's just kind of add a little bit more to our stereo selectivity. So the overall product is going to be non-stereo selective, but there's two steps to it, right? There's going to be the treatment with the mercury acetate. And that step, as you can see from the product, that's going to be an anti-addition. meaning that when we have those products, the mercury acetate and the OR should be on opposite sides of our molecule. But then when we do this sodium borohydride reduction, it's actually going to go through a radical mechanism. And similar to when we have carbocations, right? It's going to kind of take away the stereochemistry. We can add in that hydrogen to replace it in any kind of fashion. Doesn't have to be replaced right up here. We could replace the hydrogen and add it at the bottom. We could keep it at the top. So that's why the overall reaction is going to be non-stereo selective. And so let's quickly go over kind of the general mechanism. It should be relatively just a review of what we've already seen. So let's say we want to add in just a simple OCH3. And so the way we would do that is we would treat it with methanol. And then we'll do this reaction with our mercury acetate. And so our product is going to be this, right? We're going to have the hydrogen and the phenyl. And then we're going to have our OCH3. And then on the other carbon, we're going to have our mercury acetate. And notice that they're going to be in an anti-addition fashion. And then, right, our OCH3, notice that it also came in and attached itself at that carbon, because this carbon would have made a secondary carbocation. So then when we treat this with NaBH4, we're going to replace this H with this mercury acetate with our hydrogen. H, OCH3. And this is going to be racemic, right? We have a stereo center right at this carbon, or a chiral center at that carbon. So we could have both the R and the S configuration. So are there any questions on kind of the alkoxymercuration reduction? Okay. Let's look at just one practice problem. So I want you guys to take this alkene and then this alcohol. And then do the alkoxymercuration reduction. E2 and then 2 NaBH4. I'll give you about a minute to kind of come up with those products or that product. Okay, so I hope everyone is done. So then the product for this reaction, right? We're just going to be adding in this ethyl group at the more substituted carbon. And so in our case, it would be that carbon right there. So then our kind of answer would be the CH3 to CH, and we would have CH, OCH2, CH3. and then CH3 on the other end. Okay. Are there any questions on that product? Okay. So then the last bit of thing that I'm going to go over is going to be the reaction reversibility. And so if we think about these ethers, right? Something like OR, OR, they're very similar to something that we've seen, right? They're very similar to the alcohols. And we know that these alcohols, they're not very good at these substitution reactions. So there's no way we can kind of just separate this by doing some sort of substitution reaction. And why is that, right? So the reason is because similar to OH, right? When we do any kind of substitution reaction and we try to kick out that OH, what are we going to get? We're going to get a very strong base. And we know that the best leaving groups are going to be weak bases. Right? And we can kind of do the same thing up here with an ether. And so once again, this alkoxide, that's going to be a strong base. And so the only way that we can kind of reverse this reaction to go from the ether back to the alcohol and the alkyl halide is through, well, two ways, depending on what kind of ether we're dealing with. So if we have a primary ether, like ROR, right, where our both of our kind of R attachments to that ether are primary, if we treat this with a really strong acid, HBr or HI, and heat, that's actually going to reverse the reaction. And the reason behind this is because when we treat this with a strong acid, we're going to protonate our oxygen, so then it'll get that positive charge. And then our, let's say our Br minus, at our nucleophile, in these conditions, it can come back and it'll do kind of that SN2 type reaction. And so this is what's going to happen when we have these primary ethers. And the reason why we need such forcing in strong conditions is because, well, first of all, we need to make kind of this OR a better leaving group to make it so that our Br is a good enough nucleophile to come in and kick off this ROH. Now the second type of, so this reaction, it's kind of very similar to our SN2 type mechanism, right? So what if we have an ether where kind of the ether substituents, one of those sides, one of those sides is a tertiary carbon. That's not what I should do. So something like that, right? We have this tertiary group. Now you might notice that there's a primary group right here, but these same conditions that we had up here with the strong acids and heat will not work. And the reason behind this is because we could get a mix of products where when you protonate this, right, this has two ways to leave. It could either leave like this, and we form the primary alcohol, or it could leave like this, where we form the tertiary alcohol. And so the best way for it to would be in the method that's going to form that primary alcohol. Because when it does that, it's going to form a tertiary carbocation right there. And so in these conditions, what we're going to do is we're going to take our ether and we're going to treat it with a still strong, but it's going to be a more dilute acid. And then we don't need as much heat. And so then that's going to get us to our kind of protonated ether product and through more of an SN1 type mechanism, we can reform our alkyl halides and our alcohol. Okay. So are there any questions on that? Okay. So if there are none, I will stop sharing and I will pass it over to Brandon.
Can everyone hear me?
Yes.
Okay, good. Share my screen. Okay, so we're gonna start off by talking about Grignard reagents, then we'll talk briefly about organolithium reagents, and then look at how these reagents are used. So let's just get started with Grignard reagents. So a Grignard reagent is a compound in the form RMgX, Mg being magnesium, and X being a halide. So that being chlorine, bromine, or iodine. Okay, and so let's just look at some examples. We could have CH3, CH2, MgBr. Could also have something like this, MgCl. MgBr. Okay, so this is just kind of a general format of how these reagents are composed. And so now we're just going to take a look at how you form these. Okay, so if we start with our alkyl halide, so I have CH3, CH2, Br, and we react that with magnesium in diethyl ether, we will then insert the magnesium between the CH2 and the Br. So we get CH3, CH2, MgBr. So don't worry about the mechanism for really anything that I'm going to talk about today. Just kind of know basically how to form them and like what the products are in the given reactions. Okay, so here we have a polar covalent bond with a strong partial negative on the carbon and a strong partial positive on the magnesium. So I'll touch on that a little bit later, but that's going to be really important for their reactivity, that strong dipole. Okay, so we can just take a look at another example. Here's something like this. Another alkyl halide reacting with Mg, and we'll have THF as the solvent. And similarly, we get MgCl. Okay, so the solvents that you can use for these reactions are ethers or THF are pretty much the most common ones. So you want an aprotic and dry solvent, and dry meaning there's like no water contained in the solvent. And so both of these do the trick. These would be the most common ones that you'll see. Okay. So yeah, the general format of the reactions is, again, you start with your alkyl halide, react with magnesium in ether or THF, and then you'll get the insertion of the magnesium between the carbon and the halide. Okay. So now let's just look briefly at organolithium reagents, which is very similar to Grignard reagents, but this is going to be what these look like. So again, we start with our alkyl halide. We're going to react it with lithium, and this one will be in hexanes. And the product of this, we're going to get the lithium replacing the bromine and LiBr. Okay, and so again here, we have a strong partial negative charge on the carbon and a strong partial positive charge on the lithium. Okay. Okay, so both Grignard reagents and organolithium reagents are strong bases and potent nucleophiles. Okay, so if we have our reagent, right, we'll say we have this molecule right here. Okay, so this is actually going to react like this. So it's reacting as if there's a full negative charge on the carbon, right? So it's reacting as a carbon ion, and those are highly reactive. And so that's what makes these reagents so effective in accomplishing what they need to accomplish. Okay, so now we're going to, well, first, are there any questions on anything so far? Okay, yeah. So this part of the lecture is going to go pretty quickly, since this stuff I think is fairly straightforward. So let's just take a look at the reactions with those. And so if we have our, say, CH3, CH2, I'm just going to draw it as if there's a full negative charge here. And we'll have our MgX. We react that with an alcohol. We're going to get CH3, RO minus plus MgX. Okay, so really what we've done here is we have basically created a new hydrocarbon, right? So if we started, say, in the very beginning, before we even did that, reacted with the Grignard, right? Say we had CH3, CH2, Br. So we started from this and we want to create a new hydrocarbon. We react it with magnesium and ether. So CH3, CH2, MgBr, and then CH3, CH2, MgBr gets reacted with some sort of alcohol, and we form that new hydrocarbon. So that's kind of the full synthesis of the hydrocarbon, starting with an alkyl halide. Okay, so both organolithium reagents and Grignard reagents will do the same thing. Yeah, so that could have been CH2, CH2, Li, and your product is going to be the same. Okay. Any questions on this? Okay, so let's do a couple practice problems. So just take a couple minutes to do to give the products of these two reactions. Okay. Can anyone tell me what products you got for the reaction of A? Anyone? Okay. Maybe my headphones aren't working or something like that, or no one said anything. So we'll just go through this. So um, this is what we were just talking about, where we're going to have the formation of a hydrocarbon. So we react this CH3Li with methanol. And so our main products are going to be CH4 plus CH3O minus with the Li plus. Okay. And very similar for part B, just again forming a hydrocarbon. And so we have CH32, CH, CH3 plus OH minus and MgCl plus. Okay. So the last thing that we're going to talk about is reactions with epoxides. So I'm not sure that you've seen epoxides before, but an epoxide basically just looks like this. It's two carbons bonded to an oxygen, and it just looks like a little triangle. First we'll look at a Grignard reagent reacting with it. So I'll have this benzene ring attached to an MgBr. We react this with the epoxide in ether. And so these electrons right here in the middle are going to attack this carbon, sending these electrons onto the oxygen. And so the result is this. Okay, so if you'll notice that between the phenyl and the carbon, that was the new carbon right here, we've added a new carbon-carbon bond. Okay, and so that's important. So these reactions, so another way to use these reagents is to extend carbon chains. Okay, so just to complete the reaction, we have the pH CH2, CH2O minus, and MgBr plus. And so we react that with dilute acid, and then we will protonate the oxygen. Okay. Yeah. So, yes. So these reactions again are great for extending carbon chains and the production of alcohols. This is a way to produce an alcohol as well. So that's all I have for this lecture in terms of content. So if anyone has any questions about anything, feel free to ask either myself or